Okay, this is page 17 of the scheduling notes, and we are now going to start talking about preemptive schedulers. And this is section 7.4 in the course text. And we're going to look at three varieties. First, just a simple round robin, just to show you the mechanics. And then fixed priority preemptive, and then preemptive EDF. Tasks get suspended mid-execution to run other tasks. So it's that concurrency model that I showed you in section 3 or whenever that was. So the benefit, the benefit is increased concurrency. With a non-preemptive scheduler, you don't have concurrency. With preemptive schedulers, you got concurrency. If you only have one processor, as we do in the lab, then they're sharing time on the processor, but it still makes it possible to design a concurrent implementation, which is a powerful feature. So the first one is the round robin preemptive, and the first point is that all tasks have equal priority. Okay, and the task switches at the time slice end. So at the end of the time slice, the one task gets suspended and another task is resumed, and the implementation for that. So just think back, when we started concurrency, I showed 3 tasks, and first task 1 ran, then task 2, then task 3, and then back to task 1, and so on. And they weren't running to completion. They were that model where the task is an infinite loop, but they would be just suspended and then resumed later. So the implementation for this is to use a ready queue. So you just have them lined up in the queue, and that's going to be implemented with a linked list, because you can add and remove from a linked list in order one time. And to do this, we use the task control block pointers. So if you go back to the section on task control blocks, I said it records things like the task name, the ID number, the priority, but also there are a pair of pointers in there. They're TCB pointers for doubly linked lists. And what that would look like then is we're going to have a running pointer, so a pointer to the running task, and so it would look something like this. So say the task control block type has been typed F to TCB. It's a struct. So we got a pointer, we'll call it running, and it's going to be pointing to the task control block of the currently executing task. And so let's just say that task 1 is currently executing, and there's a whole bunch of other information in that task control block, but what we're interested in are the pointers, and it's going to have a null pointer because it's basically a list of 1. So this whole structure here is the task control block. Here we have the ready list, and it's going to have 2 pointers. So the head of the list and the tail pointer. So for the example with 3 tasks, next to run, let's just say that that is task 2, So that's the task control block for task 2, and then that will point to the task control block for task 3. And yeah, I'm showing this as a singly linked list. The implementation is actually doubly linked, so that when a task is terminated by another task, it can be removed from the middle of a linked list in order one time. And then the tail pointer points here for order one addition or insertion into the linked list. When we have a context switch, so say task 1's time slice ends, we want to add it to the ready list, so we'll insert it at the tail after task 3, and then we will dequeue task 2 from the head and have the running pointer point to it. So the main purpose of the running pointer is just so that you don't lose the current task that's running. You need some information about which task that is. Otherwise, everything else you need to know about the tasks are in this ready list. So on a context switch, we will enqueue the old task, or the currently running task. So in this particular scenario, task 1, at the tail of the ready list, and we will dequeue the next task to run. So for example, task 2 from the head of the ready list. And all these operations, the runtime complexity, are order 1. So scheduler overhead is order 1, so that's great. But this scheduling method has limitations, primarily that there are no deadlines, which is kind of the natural expression of a real-time system. Events happen and you need to respond by a deadline, and we can't do that with this, so it's not very responsive. And we can't approximate deadlines even with priorities because we have no priorities.